Okay, so let us start. Yeah, I think that now you don't remember anything after those 3 weeks, so it makes no sense to recall anything anymore. So let us just continue. So what we're going to construct today an associator. The title is the knižník Zama. So and for some time there'll be no associators, so everything will be like starting afresh, and things are going to be fine. So first, we're going to do something with configuration spaces of points in a plane or in complex numbers. So that, say, A is a finite set. Then I think the notation that I used was something like XA for unknown reasons, and which was simply C power A minus diagonals. So just injective maps from A into C. Now on this guy, there are some nice one forms. So I'll be denoting the corresponding points. So say if A is in A, and we have some configuration in here, some configuration which is in CA. Then the point corresponding to A will be denoted generally by ZA, is the corresponding point which is here. And now there are some nice one forms, omega AB, who are one forms on the CA for AB in A, and they are defined simply as D log of ZA minus ZB, or if you wish, DZA minus DZB. So it makes sense on this space because those points are not allowed to collide. So it's okay. Now these forms satisfy some easy relations. First of all, omega AB is equal to omega BA, that you hopefully see. Another easy relation that it satisfies is that those things are closed. Since it's D of somebody, or a multivariate function, but still it's D of somebody. And it satisfies one slightly less obvious relation, which will therefore be a proposition. Due to Arnold, which says that these forms satisfy omega AB works omega BC plus cyclic permutations is equal to 0. And how does one prove it? One just plugs it in and computes it. So in other words, it's an exercise. And now these one form are very closely related to this space, right? This space XA. So we'll not really need it, but it's good for general understanding of what's happening. So it's just some remark. But these are closed forms, so they should give us some cohomology classes, possibly 0. In fact, they are not 0. But in fact, what's happening is that when you take cohomology of this XA thingy, then it's simply the algebra or graded commutative algebra were generated by those omega ABs. And modulo, well now this A different from B in A, and say omega AB is the same as omega BA. So it's for any pair, there is this kind of generator. And just modulo these Arnold relations. So these forms somehow know a lot about topology of this configuration space. And now, okay, now we need to recall something that we met before. Sorry for that. So there was this, so recall, there was this Lie algebra that denoted by TA, this Drinfeld-Kono Lie algebra. What was that? That was something which was generated by TABs, again with the same, that TAB is equal to TBA, A different from B, so these come for any pair there is a generator, and modulo there were these infinitesimal Artin relations. Let me write them, say TAB, TCD is equal to 0 when A, B, C, D are all different. And another relation was that T, okay, maybe I was writing commas there, but okay, sometimes I will forget, it doesn't matter. And there was some relation that TA, or say AB comma C, commutator with TAB is equal to 0, where this guy is by definition is TAC plus TBC. Once there was such a Lie algebra, once upon a time. And now let us somehow combine, you see, at least those things are indexed by the same things as these things. Possibly it makes sense to look at it. So let us define this Knižnik Zamločíkov will be from now on KZ, because it's way too long to write. The KZ connection, well, what is it on? Oh, sorry, this. XA, so who's that thing? So it will be some denoted alpha, possibly we'll write subscript A if that A is needed. That's somebody who lives in omega 1 XA tensor with this Lie algebra. And what is that stuff? Well, we're just going to pair those omegas with those t's. So is the sum by all pairs, I don't know how to write it, like by all two-set subsets of this A. If I write it this way, I should probably write something like, okay, doesn't matter. I'll be probably writing it this way. TAB omega AB. Sorry for switching the order, but you can probably live with it. And okay, that's it.
So sorry, do we some? Because they are definitely similar to AB.
Yeah, so that's why. Okay, either with some over ordered pairs, then there is 1/2, or okay, with some over. This is supposed to be over unordered pairs, and then there is no 1/2. In the end, it doesn't matter that 1/2, but it would appear in some coefficient, but which, okay, whatever. So that's it. That's this connection. And why is it interesting? Because it's flat. So proposition is that D alpha plus alpha divided by 2 is equal to 0. And how does one prove it? One just plugs it in and computes it. But this time I will actually do it. Because it's possibly easier than that one. I don't know, for some reason I will do it. So proof. How about D? Yeah, I stopped writing this subscript A. So how about this, just D alpha? So how much is that? Is there anybody who is not totally sleeping? What is this? What is d alpha when you look at the definition of alpha? 0, yes, thanks. Why is it 0? Because these guys are closed.
Maybe I'm also a bit confused. What does it mean, for example, to take D of this CAB?
Oh, what does it mean? Oh, it's just we're applying D here.
Okay.
So the thing, it's like for. Sorry, I'm sort of supposing that you met things like connections or things like that you would see something like the one form with values in a real algebra, and then when people write this kind of equation, it means that they're applying D here, and then this commutator that's happening in this guy, and while here you take the product, or wedge product. Okay, so that guy is 0, so we need to prove that this thing is 0. Let's compute it. Alpha, probably divided by 2, I think it gives a better formula, but shouldn't matter in the end if it's going to be 0 anyway. Now, who is that? You see, we take 2 of these alphas and take their commutator. But very often, those commutators of those t's are 0. So things will just vanish, except for those pairs that share a common A or B or somebody. So this guy is actually, sorry if I missed some sign or two, but in the end it doesn't matter because it's going to be 0. But so it should be something like sum over all A, B, C in A, probably all, we can suppose that they are all different, of T, A, B, T, B, C, and omega A, B, wedge. Okay. I will also stop writing wedges, probably. Omega, and at some point I will just stop writing everything. Omega BC, the thingy. And so what should we should somehow probably use this relation that this with that is equal to 0, which I can write in the following way. But the thing that we see here is actually invariant under cyclic permutations, meaning TAB TBC is equal to, or cyclic permutation should be something like TBC TCA. It's just this relation. After, I think there is some switch so that there would be sign minus, so we moved it to the other side. So it's invariant under cyclic permutations. So we can average it over cyclic permutations. So we can. And this implies that, okay, this stuff is equal to the same sum over ABC with, well, the same thingy, TAB, TBC. But, okay, I will average it over cyclic permutations of ABC. So there will be something like 1/3. And then here there is this omega AB, omega BC plus cyclic permutations. But that's 0. Hooray. So it works. Was it some marvelous trick, or am I just bad at reading your faces? Okay, so keep your secrets if you. And another remark, which is this time is sort of way simpler than the one, this theorem of Arnold saying what is the cohomology of a configuration space. But I will still not prove it, but you can just deduce it from this proof. That actually flatness, okay, so this remark, that actually, so this flatness of alpha, well, this thingy, that's equivalent. It's equivalent to those infinitesimal Artin's relations. By that I mean that if you start, just say you don't remember that there ever were these kind of relations. You simply imagine that you start with any Lie algebra containing some elements called TAB, which just satisfy the symmetry thingy, and then you build this connection, this one form. Now you ask, is it going to satisfy that stuff? Well, that stuff is always zero, so the question is just, is this stuff going to be zero? And the answer is if and only if those TAB satisfy these two relations. So if you wish, somehow this Drinfeld-Konal Lie algebra is very closely related to this configuration space of points in the plane. Okay, now what are we going to do with this connection? It's a flat connection. We're going to, well, compute this holonomial or compute some parallel transport. And that is going to give us, in the end, an associator, whatever an associator is. And so, say, first observation, which is basically what we're going to do. So this alpha A is flat. So it gives us a whatever representation or a homomorphism from pi 1 of xn. We need to choose some base point in this xn, somehow some particular configuration. But let's pick any, doesn't really matter, and into the group corresponding to that stuff. The group corresponding to this TA thing. And what is this thing? It's holonomy or the parallel transport along closed loops. And so how is actually such a thing computed? Because we're going to compute it to some extent in practice, just a little bit, but not too much, but still. So how is that holonomy computed? The idea is that we'll be to define or compute the either holonomy if it's over closed, or if it's over loops, or just parallel transport if it's over curves. So we're really looking for, say, some function, a map, going, okay, look, some function going from the, sorry, this is not x, going from the universal cover of A into TA, but which I remind you how this guy is constructed. It's something very concrete. It's that sits inside the enveloping algebra complete of this guy. But what is this thing? That thing is simply the complete algebra generated by these by these generators modulo these relations. So it's Lie algebra, that's in some way more difficult stuff because there you're only using commutators. The algebra, that's simpler. There is you're simply using words, modulo these relations, and we solve the word problem for that because we know that this Lie algebra is semi-direct sum or iterated semi-direct sum of free Lie algebras. So there is nothing strange happening here. So we're looking for such a thing satisfying dg is equal to alpha times g. So that's what we do. Now, say we fix it to compute the holonomy. This fixes g unique up to the replacement g with g times some constant. G0 is in this TA constant. Just this kind of stupid linear equation. And say if you impose that G at its star, well, we need to choose one particular lift of our base point to this universal cover. We impose that somewhere it's equal to 1, and then we take a look at some other lift. Okay, and that's it. And then G is, well, the parallel transport from this star thingy. Or if you wish, if you choose some other lift of the same point, they differ by an element of the fundamental group, then the value of G on that other lift is what our map assigns, what this map assigns to this element of the fundamental group. But anyway, so the important thing, we're going to solve this equation, and it's, see, that G is an element of this algebra, which is just some power series algebra, which is multiplied with this guy, which simply contains those generators, nothing more. And we'll be solving it, well, it's supposed to exist on this universal cover, but we'll be just solving it mostly along some curve. And see what happens. We start with 1, go to some other point, possibly like the same one, after we do some braid, and we end up with some value, and that's it. So let's try to compute this holonomy in some simplest case. What is a simpler case? Probably when there is just one point, there is no connection, there's everything 0, so that's not very interesting. So when there are 2 points, configuration space of 2 points in a plane. So when example, say A is equal to AB. So in this case, this alpha there is no sum, there is just TAB and D log ZA minus and a ZB. Now let's try to solve this equation. It shouldn't be very difficult, right? So G, well, G should be just the exponential of the integral of this guy, and the integral of that guy happens to be logarithm, conveniently. And so it's exponential of the logarithm of each. But okay, I'll write it. Okay, G thingy is going to be something like exponential. It's defined on up to a constant, but I'll choose one solution, one particular. So it's exponential of TAB times times log ZA minus ZB.
Why?
What?
Why is this true?
Who asked that? It's like dg over g is equal to alpha.
Okay.
Yes. You see, we're actually we're in an algebra which is commutative. It's just generated by this t thing. So d log of g is equal to alpha. So log g is equal to the integral of alpha, who is the log of that thingy, times t. So that's why. Sorry for pretending to be threatening. Next time I will be. So that's what it really is. You see, to understand that, one should really expand it to a power series, because those things, this algebra is somehow given by formal power series in those TABs, and those coefficients are going to be powers of that log. But still, it's very convenient to write it in this way, that it's ZA minus ZB power TAB, but it means that guy. It means this stuff. We're taking power by something which is not a number, but something. So that thing is defined in this way. Okay, anyway. But what now happens if we take this ZA and ZB, and we go with the ZB around ZA, or the other way around, doesn't really matter. Let's walk with ZA, ZB. We go like this, or we simply just exchange those ZA and ZB. We make this turn. What happens then? Just look at what happens in this case. So this will give us exponential e and pi I times TAB. There's this change in the log, or if you wish, if I denote this, z will be this ZA minus ZB, and we're integrating dz over z along this stuff, like this half circle, and we're getting this pi I thing. Okay. So it means that now when we're exchanging two things, we're getting something like that. If you make a full turn, then we've got 2 pi I, naturally. But why am I writing just this half turn? Because once upon a time there was that associator. Now let's try to recall what an associator was. Greenfeld. So there was somehow either full definition or fully spelled definition, or just definition in terms of generators and relations, so to say. But this full thingy was that we wanted to, there was this groupoid PABA, those were parenthesized braids. That's a groupoid. But if you just pick one particular object, then the automorphisms of that object is simply this pure braid group. So it's this pi1 thingy, PBA. So if you cover that thing, it's very closely related. So those are parenthesized braids, and we want to go from this groupoid to the corresponding group. And plus, so we want to have these kind of groupoid morphisms, which is simply a group, which is also compatible with operatic compositions or with operatic substitutions. So like this was probably called, phi, little phi A, compatible with substitutions, but whatever that means. But in particular, there was one thing when we just take this braid, AB, BA, that's something that belongs to BAB, AB. It's a morphism connecting AB with BA. It's this half turn. This will be sent necessary to exponential of something, some number, which we call mu divided by 2 times TAB. And this mu was by definition the whatever weight of the associator. And we're just getting to an associator here, and its weight is going to be 2 pi I. Going around, we give you pi I, which is 2 pi I divided by 2. And now this, again, maybe you recall, or well, let's pretend that we're recalling that this phi is fully determined by knowing what's happening here. So what's happening with braiding, with a single flip, which is just given by a number, this weight. Just by this mu. And by the image of this A, B, C, this single rebracketing, which is then some capital phi, which happens to be just in T, A, B, and T, B, C. And so this phi actually leaves whatever is our base field, which in our case is going to be complex numbers, in two variables, two non-commutative variables. And now we're going to extract some phi from here, and then there will be a theorem saying that it is indeed an associator. So let's try to do it. So constructing something that is going to be called phi kz, or it lives in C, x, y. So this x is like this TAB and y is TBC, just so that you don't have to write too many indices. So how does it work? See, the idea is to do this. So we start with the configuration of, let's say we have ZA, ZB. Okay, let's put it this way. ZA is going to be 0. ZB is going to be 1. Sorry, ZC. And it's only ZB who is going to move. So we take some curve in the configuration space, curve or path in X ABC, which is given by ZA is equal to 0, Z1 is equal to 1, and then this Z whatever. I should just stop writing, as I said. And then this ZBT, it should go from 0 to 1, so I probably write something like T. And we want to take the holonomy of our connection. And take the holonomy of our alpha, or if you want ABC, along this path. So let's just see what happens. And
whether T is 0 and 1, ones go on the side, but in configuration space we remove the diagonals. In the configuration space we remove the diagonals, so, but at T is 0 and 1.
Right, so I was trying to be sloppy and then come back to this point. But yeah, so we cannot take this entire path from 0 to 1, but we need to take it from T who is starting at some epsilon and ending at some 1 minus epsilon for some small epsilon, then try to take some limit or something like that. But I'm shocked that somebody pays attention to. And it's not me, unfortunately. Okay, so let's see what's happening in this case. See, I will call this. Let's use this notation. That is X is TAB and Y is TBC. And since ZA and ZB are not moving, and it's only this ZC, it's only this ZB who is moving, I will call now this ZB simply by Z. ZB. So our alpha is going to be, well, in principle, it's the sum of 3 terms, right? Per now there are three pairs. But just along this path, ZA and ZC, they are not moving, so the term omega alpha is something like TAB, which is simply X omega AB plus Y omega BC plus, and we don't have notation for this guy, omega TAC omega AC, but this term is 0 on the path. So when ZA is equal to 0 and ZC is equal to 1. And so what it is equal to, it's something like X times DZ over Z and plus Y times dz over z minus 1. That's what's happening. So now it's just one form in one variable, so it looks somewhat nicer. And we would like to take this holonomy that is, we're solving our ordinary differential equation or using, I don't know whether you know whether we made this kind of notation, but it's just notation for what it is. So we take the holonomy is not denoted by path ordered exponential from, from epsilon to 1 minus epsilon of this x divided by z plus y divided by z minus 1 dz. Now, we would like to take, that's the holonomy. Now we would like to take the limit for epsilon going to 0, and naturally that limit doesn't exist. Why doesn't it exist? Because when you're going to it epsilon to 0, then this term is starting to diverge. And here is this term who's starting to diverge. But we can at least hope that, say, when we go with epsilon to 0, it's only this term which is making troubles, and we can just ignore that stuff. And simply, let's try to regularize it or multiply it by something which removes the divergence. Meaning, we would just take the exponential of this thing and now multiply it by the inverse of the exponential, and the same stuff there. So let's try to take exponential, and just in case I don't make a mistake, okay. Well, let me just write it already with this. Epsilon power minus y. This is epsilon power x, which is understood as this exponential of x times the logarithm, right? So this is x log epsilon. So that's at least what hopefully is removing the singularity. And now, so the holonomy itself is only this stuff, right? It's the holonomy along the path. The holonomy doesn't have a limit, but if we somehow try to remove the divergence by writing these things like that, and take the limit, epsilon goes to 0. It's not entirely clear that the limit exists, but it sounds reasonable that we somehow killed, hopefully, the singularity. And now let's call this phi kz x and y. And now first of all, there's the proposition the limit exists. And for the proof of that, so there is an alternative way how to write the thing. So let us, or it's equivalent to saying to this thing. So there are solutions G0 and G1 of this dg, where I is equal to alpha, where alpha is this thing. Gi, where all those gi's go from c minus 0, 1, that's where our z lives, to whatever, to c xy, and such that we see that parallel transport is obtained by taking a solution who is equal to 1 at epsilon, then we let it evolve and look at what's happening at 1 minus epsilon. But then we need to remove this strange thing. So it's possibly better to start with a solution who is not equal to 1, but who is rather equal to that stuff. And this gives sort of even a cleaner definition. I should probably, we'll have break soon. We'll just finish this thing. So we want that G0 Z is asymptotic to Z power X around Z is equal to 0, which means that G0 Z is equal to that stuff, Z power X, and times something which is holomorphic. Holomorphic in Z, and which is, this thing is moreover equal to 1 at Z is equal to 0. That's what it's supposed to be. And this G1 Z is asymptotic to 1 minus Z power Y around Z is equal to 1. So you recognize this thing. That was the solution for the KZ equation, or for just that thing that dg is equal to alpha times g. In the case when there were only 2 points. Now we have 3 points, but somehow what we are alluding here, that there are those 2 points who are very close to each other. There's the 0 and that z who is close to that guy. And so that thing which sits at 1 doesn't influence it too much. Like this really hardcore stuff is happening around this black hole and whoever, this small planet somewhere. Yeah, it doesn't do much. So that's stuff. And now the statement is that these G's exist. G0 and G1 exist. And why is that? Just take this expression. You take this expression where this is a holomorphic function with values in t, but still a holomorphic function. Plug into the G0 is equal to alpha G0, and see that it has a solution for the holomorphic thingy. This holomorphic Z exists. That you get another ODE. You just plug this in, remove that stuff. You get another ODE, and it's a nice ODE that you can actually solve. Solve, I mean solve step by step, so to say. That you can see that it does have a solution. You construct this as a power series, if you wish. That's not. At first, it might be not obvious. Then it starts looking extremely obvious. But then when you plug it in, it's slightly less obvious, but it still works. And so it's again an exercise. It's a calculation which is an exercise. Yeah, and I should now really stop. And so finally, this phi kz is equal to, we have 2 solutions, so they should differ just by a constant. One of them should be just the other one multiplied by something on the right. So phi kz is, and if I knew, can somebody help me? How I should write it? This should be like G0 times G1 inverse, but in some particular order and some particular G1s. So let's see, we start with 0. So it's probably G1 inverse G0 or something like that. And that's the end of the proof for the fact that this phi kz makes sense, that this limit exists, just because one can construct it in this way. Now let us have a break. Okay, so let's now get to it. Now the main statement is that this phi kz that I just erased is an associator. So a theorem that Drinfeld So that stuff is a associator of weight. Two pi I. I guess he didn't call it the Drinfeld associator, but let's use this notation. And now you'll be surprised now that when I add here to prove that it's just a sketch, because that's supposed to imply the previous proofs were not sketches. So, or say, what is the general idea behind that? Well, there are some technical details that would take way too long, probably. But the general idea is relatively simple. So we actually want to construct when this full definition of an associator, we want to construct that phi going for every A and check that it's a morphism of operands, that it's compatible with substitutions. And each of these are going to be constructed using the Knižing-Zamolčíkov connection, just using parallel transport. The parallel transport of this connection. And so first of all, so how does it go? First of all, for any object that is a parenthesized permutation of elements of our A, for any object, how do I call it? Let's say pi. It's a parenthesized permutation, so I could call it pi. So for anything like that, I'll assign some point in this XA. And how is it done? Let me show you just an example, and that should be enough. So example, first of all, we need to choose some small and say positive epsilon, and say to A, B, C, D thingy. So to this particular object, we assign the following configuration. So there would be ZD, which I place somewhere at wherever, doesn't matter, but now there is ZA and ZB, ZC. And what is the rule now? The rule is that, say, the distance here between ZD and, say, the center or something of this group is equal to 1. Now, in the next group, in the next parenthesis, the distance is going to be epsilon. That stuff is epsilon. And finally, for the innermost thingy, it's going to be epsilon squared. And I should also specify exactly where I'm placing it. So say here is the point 1, and here that's 0. Like we're in C, right? So we're in C, but actually everybody lies on R. So that there is, for this parenthesized thing, it's now decomposed into two clusters. From the outside, one contains just D, the other contains whatever is the thing. Now those two clusters should be around 0 and 1. Now you look at each of those clusters, they are they are now decomposed again into some subclusters. This one is not decomposed into anything, but this one is decomposed into A and BC. And now they should be separated. You split them apart, but just by epsilon. And then you go on and on and on and do something like that. Yeah?
Sorry, so the thing in the middle is the middle or the center of mass, or the
Let's just keep it this way, and then we'll actually have a precise definition a tiny bit later. Or let's put it this way, that we always somehow want to put that cluster at 0. But how we do it? We now move to epsilon half from 0 this way and that way, and now we're putting the remaining cluster at this point and at this point. Now this cluster is already only 1 point, so we put it directly there. This guy is still a cluster, so we need to move by epsilon squared divided by 2 this way and that way, until we somehow land into something. So it just gives this general idea of representing this parenthesization by distance, by order of magnitude of that epsilon. So when epsilon goes to 0, then those things start colliding, but they collide. The speed of collision is according to how many nested parentheses there are when they go together. Something like that. Now to any morphism, say from pi 1 to pi 2 in. So what is that morphism? That's actually a braid, right? Braid respecting colors of those strands. So what do we do? The braid is a path in XA. It has a path in XA. We know where to start with that braid, we know where to end it, and then we do our braiding thingy. So we have a path in XA, we have our connection, we can compute the holonomy. So to this, we assign where we take the holonomy along the path. But if you remember, that's what we were doing with this associator. Right? But there was this particular example. We had this A, B, C thingy, and then there is a BC. Just imagine this is the time. Oh, here is plane, here is plane. Oh, these points, they actually leap on the real line. And now with time, the thing remains. It's only this guy who moves. So it's a particle case. And we had to remove that some singularities. If we want to take limit epsilon goes to 0, then that holonomy would diverge. And so we need to regularize things. So how do we do it? So there is some regularization term depending on this pi 1. And then a regularization term depending on pi 2 inverse. And finally, we take the limit epsilon goes to 0. And what is that regularization thing? Where we again just look at so what is let me again say spell it for this reg A B C D. The thing. So what is it? let's think about it, what's happening here. See, the worst thing that's happening here is that we're letting this, ZB and ZC collide very, very closely. They are going up to this epsilon squared. So when they start doing it, so imagine that we start colliding them, then sooner or later they stop caring about other points. They start caring mostly about just themselves. There is the singularity, and we need to remove that guy. And so there would be this epsilon squared and power T, what's it appear here, power T BC and times. Okay, so we already let those things collide. Now let us move ZA close to this cluster, but only to this distance epsilon. So this ZB and ZC, they act like one man, but this guy goes close to them. So we need to multiply it by epsilon, and here there is T AB plus T AC, or if you wish, I can call it TA BC. So that would be some of the rule for constructing those regularizations. That for each parenthesis, you look at what is the order of epsilon appearing there. So you put the epsilon power that order, and now right inside some t, and t who is happening, it's always somehow epsilon power n, whatever n is the order, how many parentheses we had to come through. And then there would be something like t a1, comma a2, where these are subsets of A and containing those elements who are in one side and on the other side. So these are subsets. So just imagine that you have some parentheses, and here there are letters containing this A1, and here there is A2. So you'll be always seeing things like that. I need to go through every parenthesis and write the product of all of that. And write that expression, and now the limit exists. So this. And the only reasonable proof I can imagine is repeating the proof that I showed you for existence of the associator. So one needs to look at some solutions which have some asymptotic behavior, and it becomes sort of impossible for me to write down. So let's just imagine that when we do this, then we get this limit. And so this gives us a, and we have a groupoid morphism from PABA to TA. Is it okay? Yeah, it is okay, because you see, there is this holonomial that we multiply by some stuff, but when we start multiplying things, we always would be taking reg times reg inverse for the same configuration. So as long as this limit exists, it certainly is a groupoid morphism. But there is still a question. The question is whether it's compatible with operatic substitutions.
Sorry, can I ask you, so the objects here still depend on epsilon?
Objects don't depend on which objects? Objects of PAB that contain no epsilon whatsoever.
Right.
No, it's like that we chose some epsilon to assign to each object a sort of base point in this.
Yeah, but this.
So that base point, it depends on epsilon.
Okay.
So without taking the limit, everything there depends on epsilon. And so for each epsilon, we would have that morphism is really given for each epsilon. That's fine. But then the statement is that we can take the limit epsilon goes to 0. And that's the thing that we're going to use. So this it's true that just for having those groupoid morphisms, they are defined for every epsilon, for every non-zero epsilon. But the one that we're actually going to use is the one which is given by the limit. Why is that? Because if you use non-zero epsilon, they are not compatible with opera decomposition, but that limit is compatible with opera decomposition. So let's finish that. So why is phi compatible with the operand structure or with substitutions? Just to remember at least something about those substitutions, that if you have, say, one parenthesized braid, another parenthesized braid, what can you do? You can replace one strand in the first braid by the second braid, which is made very thin, which goes around this one strand. That's what we're going to do. How does one encode that in terms of those configuration spaces? So let's look at the map. So consider the map is going from, now, say, A, B are finite sets. We take some A0 here, and we want to replace or substitute B for that A0. That's what's happening. And the map is going from XA times XB to configurations that where this A0 is replaced by B, so to X A minus A0 disjoint union B. The map depends, well, depending on epsilon. Everything depends on epsilon. You want to take the limit, epsilon goes to 0 in the end. The map is obtained by, so you say that when you have a configuration of all those ZAs, A in A, and ZBs, B in B. So what is the resulting configuration here? So we keep all those ZAs for A different from A0. But then this ZA0 is going to disappear, and it's supposed to be replaced by a cluster of those ZBs around the ZA. So there would be ZA0 is no longer there, but it's going to be this plus epsilon times ZB for all B in B. Now, okay, that's the map. So somehow, just imagine that you have some configuration of those ZA1, ZA0, ZA1, ZA2, and another configuration, ZB1, ZB2. So that stuff is now being mapped into, I'll try to draw the same stuff. ZA1, ZA2. You remove that point and replace it with that stuff which is somehow close around that point. So this is ZA0 plus epsilon, ZB1, and that would be with ZB2. Yeah, the map is not actually defined. That was your question, I guess. So there is this wonderful notation that I recently met. It's defined only on some open subset. The trouble is that of course, these points might not be all different. It might happen that you have collisions, But what is true is that for any particular configuration, when you go with epsilon to 0, when for sufficiently small epsilon, things become okay. So there is some neighborhood, I know, blah, blah. There is something can be said about it. So the map is not always defined, but it's sort of defined for epsilon small enough when understood in the right way. You still have a question?
Yes. So can it be that there is a point near A0 which is also in epsilon distance?
But
Put epsilon to some bigger.
well, and in that case, you take even smaller epsilon. I just said that for any configurations, there is epsilon small enough such that it starts being.
Yes, okay. But
It is the only thing I can say. Yeah, you cannot use the same epsilon always.
okay.
There is no uniform epsilon that you can use, but it's only locally uniform or something. Okay, so that's life. And now what's happening with KZ connection when you do this replacement? So let's call it this. Okay, it's actually somehow opera decomposition, so I'll use little o A0 for this map. It depends secretly on that epsilon. So what's happening with KZ connection when we do this substitution? Or so to say, what's happening when you have some points and then there is some cluster of points close to each other that somehow wants to move close to each other and everything's happening there. And roughly speaking, this KZ connection parallel transport, we remember that something's happening here, something's happening around, but this cluster will act like one man with respect to any other of that point, any other point. So what's happening exactly? So O A0 star of this alpha, whomever that is, well, this guy, is equal to, so what do we see there? We'll see certainly the sum of T A1, A2, omega A1, A2, over all pairs that are in A. Then there would be some, you see, I should probably write it somewhere. If you remember this omega, I don't know, A1, A2, what was that? This was like D log Z A1 minus Z A2. When you do this kind of substitutions, or maybe I'll write it, okay. When you do this kind of substitutions, we would see there's something like D log, there would be something like A0 plus epsilon ZB1 minus ZA0 plus epsilon ZB2. That's what's happening. That's what's happening for these points, right? Those that were substituted. You see what happens? This ZA0 disappears. And now there's this epsilon under log and moreover under D. So epsilon disappears as well in the end from D log. Epsilon is a constant. So you can sort it out of the log and there is D, so it gets killed. So that stuff remains what it was. So for these pairs, you're having your wonderful T B1, B2, omega B1, B2, B1, B2, and B. So now we took care of those A pairs, those somehow B pairs, but there are now also those pairs which goes between A's and these composed points. So what's happening there? So there is plus. And the thing that we'll see here is that there will be sum over A in A And here there is T A comma B omega A0 plus O of epsilon. You see what's happening? Yep.
Should there be A, but without A0 in the first time and in the...
Yeah, without A0. So you see what was now happening? We're taking the say for each A, say for A1, we would be taking the sum over all points entering here. But in that D log, there would be only very small movement there. So that was going in this O epsilon. We can replace each of those points simply with the center, so to say, with that A0, that was A0 that was there. That's what's happening here. And now for the coefficient, we're getting the sum over, well, that stuff is defined as the sum over all B's in B. TAB. So that's what we're getting there. So in other words, our connection is compatible in this sense with this opera decomposition, but only up to that term. So this is this ugly term, which is just there. We really want to have this equality, that the substitution goes to substitution in the sense of this Drinfeld-Kono-Lie algebra. The substitution is defined in that way. That put there set means taking the sum over all elements of the set. That's why we need to take that limit epsilon goes to 0 if we want to achieve something, and it works. So to finish, so this alpha thingy is compatible with the substitution, say, in the limit epsilon goes to 0. And that's the reason, and that's why also. And so that gamma T, which was defined as the limit, is also now here I'm actually, so that is the general reason. Now here I'm cheating quite certainly, because you see in the definition of gamma we were not just simply taking the parallel transport. If the connection is compatible, then the parallel transport would be compatible, but that gamma was not defined only as the limit of parallel transport. It was defined as the limit of parallel transport multiplied with some regularization terms. So I need to show that also those regularization terms, they don't cause any harm. So modulo possible troubles with those reg pi's, but it turns out those regularization terms are simple enough that nothing bad happens. So, but it still works. So let's call this the sketch of the proof. So I agree that this was really quite sketchy. So there were some parts really missing in this proof, but at least you might have some impression of why it should work. To cover this up a little bit, let's try to make this KZ associator more concrete. That is something really reasonably easy to compute. So how to compute? phi kz. First of all, you see, it's certainly that phi kz, since it's a formal power series, then necessarily it's just a thing which is of this form, that it's that is sum over all words, CW times W. These are words in X and Y, and these things are complex numbers. Any formal power series, I guess, looks like this. And so we want to compute those CWs. So let me try to, okay. What was it? I need to write it down again. So phi kz xy, there was some limit. Epsilon goes to 0, epsilon minus y, and there was this holonomy px integral from epsilon to 1 minus epsilon x over z plus y over z minus 1 dz, and then there is epsilon power x. Now there is this ugly limit, but if you consider only words that start with x and end with y, then these terms make no harm there, and also that integral is going to just converge when epsilon is sent to 0. So for words w's starting with x and ending with y, there is no problem. Putting epsilon is equal to 0, so I have probably some example here. Yeah, let's say, for example, if we take w, which is x, y, y. So how does one ever meet such a word from this expression? Well, this doesn't contribute because that would produce some y. This doesn't contribute. We should take just thing coming from this stuff, take the limit epsilon goes to 0. We can already put epsilon equal to 0 and go to 1. And so what we meet there, we get that CW is the integral, where there is this ordered exponential, which means that, well, there's integral over some ordered, which is Z1, Z2, Z3 smaller than 1. Yeah, and the last one that we're going to meet, well, this composition is written from right to left. So the last one that we're meeting is x. So that's why there is 1 over Z3. The one that intervenes before, there's Z2, that's going to be 1. So there's going to y, so it's 1 over Z2 minus 1. And then there is another y, which gives you 1 over Z1 minus 1, dz1, dz2, dz3. So these are those things that we're computing here. just these kind of integrals. You see, just each x is replaced by this 1 over z, each y, because it comes with this 1 over z, each y is replaced. You get this 1 over z minus 1. That thing, they enter in the same order as they're here, and it's just that this variable is always the biggest one, then the next, and so that's why this order is reversed if I want to keep the order as is here. So we're integrating over simplex like that. That's the definition of this stuff, if you wish. And that's how you, well, that's in the end how you solve that. Well, this thing is defined as a solution of some ODE, linear ODE, and that's how you solve this ODE. You just by the successful approximation by iterated integrals, right now, Picard approximation or whatever is that thingy. Yeah, I'm still teaching analysis 1, you see. So that's the stuff. And now we still have some time. Yeah. One can actually compute it. You see, these are not all words, but for other words, it's then easy to determine once we know these words. And now there is some nice theorem. Sorry, it's used for using paper, but it's probably better if I use paper. So there is a theorem which just says that one can compute this integral. The theorem is, well, there are surprisingly big names for such a theorem. So there is Kontsevich, who say actually computed the integral, and then there is Le and Murakami, who then actually observe that those are those integrals that enter into this KZ associator. And the theorem says, oh, let me write it here. That if our word how is it that it's okay x km minus 1 times y, so meaning that there are km terms here, and there is x km minus 1 y, so there are km minus 1 terms here times etc. times x k1 minus 1 y. There are k terms here, k1 terms here. So some of those k's can be equal to 1, I guess, except for this one, right? So here k should be at least, km should be at least 2 if you want to have x here, but otherwise here there might be some repeated y, so that's when there would be no power of x. Then the CW is equal to, first of all, that's a not very nice order to have z minus 1. So it's way nicer to have 1 minus z, which does what? Which brings in a sign. How many signs? As many as those y's, or meaning m. So there is minus 1 power m. It's to be expected. Just that's the sign of the thing. And then there is a zeta k1, k2, km, where this is what is called a multi-zeta value. So this is the sum over what? 1, or okay. Let's put it this way. N1, which is smaller than N2, smaller than Nm, and 1 over N1 K1 Nm Km. That's the definition of this, what is called multi-zeta value. So in particular, if you have just C x k minus 1 y, then this guy is going to be minus zeta of k, which is the ordinary zeta function. And say it's very easy to prove it. It's just a computation, but probably it's not very easy to prove it in 1 minute. But at least I can tell you something which how to determine all the others CWs, because this is not for all words. These are only for words that start with x and end with y. So that's the end of the theorem. So we know also, so we know this is something true for any associator. If you remember, this phi is somebody who is group-like. This is one thing. And we also know, which in particular means that phi is equal to exponential of some Lie series. Some L xy, which is a Lie series. And that Lie series is one more thing we know, that this Lie series contains no x and no y. It only contains brackets. It doesn't contain any linear term. I know that it happened like 3 weeks ago, but we actually learned this stuff. So just believe me that this is true. And so from this implies, so just this statement here implies, if you think about it, that C x power n is equal to 0 and cy power n are all equal to 0 for all n. There is no way how we would get from this just power of x if everybody here contains at least one y, right? Because no commutative would ever contain only x's unless it's 0. Okay, and now so using this and also this wonderful formula, delta phi is equal to phi tensor phi, one can determine find all CWs using this, and this, and this Koncevich-Murakami theorem or formula. One can find all of these, and how to do it, at least in special cases, that's going to be an exercise. Just plugging into formulas and see what's happening. Okay, so this KZ associator is, as long as you find these numbers not terribly mysterious, then it's not a terribly mysterious thing. It's a very concrete gadget that will use them. Okay, so thanks.